Hello, today we are checking on a gas turbine and the gas turbine plant and how we calculate or we solve the problems involved or associated with gas turbine. Now, today we are checking on an open gas turbine plant and this is the question. Then, in an open gas turbine plant, the air from the compressor passes through heat exchanger, where it's heated by exhaust gases from LP turbine. The HP turbine, that is high pressure turbine, drives the compressor only. Exhaust gases from high pressure turbine passes through the low pressure combustion chamber, then into the low pressure turbine, which drives the external load. We are given the following data: overall pressure ratio, which is 10:1, isentropic efficiency of compressor 0.85, isentropic efficiency of HPT. Then we are given isentropic efficiency of LPT 0.88, heat effectiveness, which is 0.75. We are also given the temperature entering the HPT, that is high pressure turbine and low pressure turbine, at 700 degrees Celsius each. Then we are given atmospheric. This is atmospheric pressure and temperature are 1.01 T bar and 25 degrees Celsius respectively. We can take now CP for air. We are given is this one, and we are given the index for compression for air, which is 1.4. Then CP for gas and the compression ratio or compression index for expansion index, sorry, for the gas. Then we are required to sketch plant and TS diagram, and we determine the pressure of the gas entering the low pressure turbine and overall thermal efficiency. Now, I have just sketched the plant diagram and a TS diagram for you, and this is the result. We have the plant diagram and we have the TS diagram. When we explain from the term or from our diagram here, then we relate with our question here. We are told that the air from the compressor passes through heat exchanger. This is the compressor. Then the air from this compressor, it is, remember, this is the air getting in. These are free air getting in or atmospheric air that is taken in to the compressor. Then it is then taken to, they say that it passes through the heat exchanger. The heat exchanger, this is our heat exchanger. You say that this is our heat exchanger. Then it is heated by the exhaust gases. The exhaust gases which are coming from LPT. This is LPT. So the exhaust gases are coming from this area. Then they enter to the HE, that is heat exchanger. Then this heat is heating the temperature here. So the temperature from 2 to 3, 3 has high temperature than 2. Then we are told again that the temperature entering the HPT, that is high pressure turbine and low pressure turbine, is equal, and that is 700 degrees Celsius. What does it mean? It means that since we are told that the gases, the exhaust gases from high pressure turbine passes through the low pressure combustion chamber. So these are low pressure combustion chamber. Then we are told that the exhaust gases, so they are heated here. It means that for 4 and 6, we have equal temperature. So we have to include CC1 here. Then we have CC2. So CC1 here, it's for the high pressure pressure turbine, that is combustion chamber, and this is low pressure combustion chamber. So we have two combustion chambers. Then we are told that the exhaust is coming from here. We are told again that the LP, that is low pressure turbine, drives the external load. This is an external load, and the example of an external load can be a generator. Then now, out of this one, we can go to our TS diagram. We explain a bit about the TS diagram. This is our TS diagram. And from this TS diagram, you see now the temperature or the air, free air is getting in here. Then isentrophically goes to the compressor. Then it rises for the actual. This is the actual rise of the temperature. Then from here now, due to the exhaust gases from the LPT, which are eating this temperature, it means that this temperature is high. So it rises gradually to 0.3. Then again, from here, we have CC1, that is combustion chamber for high pressure. Then it is raising the temperature for T4. Then again now, the temperature goes down isentrophically to HPT. Then again, it rises from 4 to 5. Then from 5, the temperature heated by CC2, that is low pressure combustion chamber. Then they go to 7, where 7 is an exhaust which is coming to heat exchanger, then going away. And this is it. Now we have the pressure. In terms of pressure, we have pressure 2 equals to pressure 3 equals to pressure 4. If you can check well on our TA sketch, we have 2, 3, and 4. So those are the pressures. Then we have 5 and 6, that is P5 equals to P6 for what? So in this case now, we've said that pressure which is here equals to pressure which is here at a high pressure turbine stage, and this is low pressure turbine stage. Now we go back 12, P1 equals to P7 equals to P8. Now what we are required to do is step number 1, we have to calculate all the temperatures. So we calculate temperatures of entire plant. Now we have the entire plant, that is turbine plant, and we have to calculate the temperatures. Okay, now we start with our first temperature. Before we start from the temperature, now we can get the data where we are going to convert our temperatures into Kelvin. So we can go for T1. We find our T1. Our T1, it is the atmospheric temperature, which is 25 degrees Celsius. We have 25 plus 273 to convert into Kelvin, and this will be 298 K. Remember, this is now our T1. Then this is our T2, this is our T3, this is where we get T4, we get T5, we get T6, we get, so this is T2S isentropic, this is T5S, and this is our T7S. So we have to calculate all the temperatures. Then we have T4 equals to T6, which is 700 plus 273 to give you 973 K. Now we have those temperatures. Now we go and calculate for T2S. we get T2S. Now T2S is given by T2S over T1 equal to P2 over P1 multiplied by the index, the compression index for the air, minus 1 over air. So we can make T2S the subject. T2S will be equal to T1 multiplied by P2 over P1 into Y minus 1 over for air. So now we get T2S. We substitute, we have T1, our T1 is 290, 298. Then we multiply by P2 over P1. Remember, we have the overall pressure ratio, which is 10:1. So this becomes 10. Then we have to get is to power 1.4 minus 1 over 1.4. And our T2S temperature, that is isentropic temperature from the compressor or for the compressor, will be gotten as 595, 595 from our calculator, 595.3. Okay. Again, now we go ahead and look for T2. We have T2S, so we go for T2. And T2, we are now relating, that is isentropic efficiency of the compressor, which is given by T2S minus T1 over T2 minus T1. So we can make T2 the subject of the formula. So our T2 will be equal to T1 plus, it will be equal to T1 plus T2S minus T1 over the efficiency, which is compressor isentropic efficiency. Now we can get T2 by substituting T1, we have 298, then plus we have T2S. Our T2S is 595. Remember, this one, this is our T2S, which is 595, 95.3. Then we minus T1, which is 298. Then we divide by the compressor efficiency, which is 0.85. And after calculation, you get that it is 647.8 K. And this is our T2. Then we go ahead and we find, we look for T3. Our T3, we are not looking at it now. We are not solving it now. But now we go for T4. We know T4 and T6 are equal. So we have the temperature for T4 and T6. So we go for T5. For T5, we find the temperature T5. And our T5 is given by, now we are relating here, that is work done by high pressure turbine, we multiply by the mechanical efficiency. Why would we multiply by mechanical efficiency? Because of the shaft. Remember, this is our shaft, and we are connecting the HPT drives the compressor. So we have the mechanical efficiency from the shaft. That's why we are just getting it multiplied by mechanical efficiency, which can also, or which is equal to the work done by the compressor. And this one is, so work done by HPT is given by MCP for gas. Remember, we are here from CC1, the air is burned, then it becomes the gas. That's why we are saying we are taking the MCP for the gas. This is mass. Then into, then here we are taking T4 minus T5 because of what? T4 is higher than T5 in terms of temperature. Then this will be multiplied by 1, the mechanical efficiency. We are not given the mechanical efficiency, so it means that it is driving it at 100% efficiency. So 100 divided by 100 is 1. And this one is equal to mass Cp for air from the compressor. Then we have T2 minus T1. I hope we are together. Then we can go ahead and find by m, that is mass, is common. So we can get T5 as the subject of formula, which will be given by T5 will be given by T4 minus Cp over Cpg, then T2 minus T1. We can substitute what we have. Then T5 will be equal to our T4. We said our T4 is 973 minus Cp for air. We are given as 1.005. Then we divide by 1.15. We say this is 1.15, sorry. This is 1.33. Then we have T2. Our T2 was 647.8 minus T1, which is 298. And when we calculate here, we are getting the temperature T5 is 667.3 K. Then now we can go ahead and we find T5S. Now we get T5S. We get T5S. Now our T5S, which is isentropic, we can say for T5S, which is isentropic expansion. Now we can get it from this formula, that is, now we have the compressor efficiency, that is high pressure turbine efficiency, which will be equal to T4 minus T5. This is over T4 minus T5S. So we can get T5S, we can make T5S the subject formula, and our T5S would be equal to, our T5S will be equal to T4 minus T5 over HPT, that is efficiency for high pressure turbine. And we have T4 973 minus T4 is 973 minus T5 was 667.3, then over 0.86 from our question. Then this one, when you calculate, you are getting T5S is 617.5 K. Now we continue and go for T7S, which is isentropic. So, and this one is given by T6 over T7S equal to P6 over P7. Then index for gas minus 1 over index. But we know something. We can find T7S, the subject formula. So we will say T7S will be equal to T6 over P6 over P7 into, then we have YG minus 1 over, so we have this one. But we know P4 over P5, we multiply by P6 over P7, it will give you the ratio, that is the overall ratio. We continue and have our P4, P5. P4, P5 can be given by T4 by T5S into for the gas over by G minus 1. Then now we can calculate our T4 or our P4 over P5. And this one will be equal to T4 is 973 over T5S. Our T5S is 617.5. Then we have the reciprocal. This is, remember, this is the reciprocal of the compression or of the expansion in terms of P4 and P5. And this one will give you into 1.33 over 0.33. So now when you solve this one, you are getting our P4 over P5 as 625, 6.25 bar. It is 6.25 bar. We can continue and find now P6, P7. So we make P6, P7 the subject formula. So we'll have P6 over P7 to be equal to RP over P4 over P5. So our RP equal to what? So which is equal to 10 over P4 over P5, which is 6.25. And this one, in our solution, we are going to get it as 1.6 bar. Our P6, our P7 is 1.6 bar. Then we go back and we substitute to now T7S, which is equal to T6 over our P6, P7, which is 1.6 into G minus 1 over G. That is for gas. And this one becomes T6 is 973 over 1.6 into 0.33 over 1.33. Now, with this one, when we work out, we are going to get is 866 K 47S. That was the isentropic expansion in that case. Now we go and get T7. 47. 47, we are going to relate the isentropic efficiency of LPT because we were under the LPT. Remember, we are told that the isentropic efficiency of LPT is 0.88. So we are going to work out on that one. That is isentropic of LPT will be equal to now T6 minus T7 over T6 minus T7S. Now we make T7 the subject of formula, and we are going to get as T6 minus LPT into T6 minus T7S. Now we substitute what we have. We have T6, which is 973. We minus the efficiency for LPT is, we have said, is 0.88. Then our T6 is 973. We minus T7S. Our T7S is 866. Then when you work out this one, you're going to get 870, 878.8. 878.8K. This one is for T7S and T7. Then now we can go back and look for T3. Now we can go back and solve T3. Now the T3, in this case, let's solve T3. We are going to relate now. We have the effectiveness, the heat effectiveness, where we say for T3, we have the heat effectiveness, which is equal to T3 minus T2 over T7 minus T minus T2. Now we can make T3 the subject formula. So T3 equals to T2 plus, now the heat effectiveness, then into T7 minus T2. So we can substitute what we have. We have the values for T2, we have the value for T7 and T2. So T3 will be equal to, our T2 is 647.8, then plus 0.75 into T7 878.8 minus 647.8. Then when we work out this one, we get T3 as 821K. 121K. Then now we go to question Roman 1. Says Roman 1 is saying that the Roman 1 in our question says that we have the pressure of the gases entering the LP turbine. The pressure of the gases entering the LP turbine. And we can go back and check on the pressure entering the LP turbine in our case. The pressure entering the LP turbine, you say that it is P6. Remember now, the P6 here, it's entering into LP turbine. This is our LP turbine, LPT. stage. So this is the pressure P6. And now we can recall that from that point we can get P6, or P6, which is pressure entering LPT, pressure entering LPT. So now we have to remember we said that our P6 over P7 equals to 1.6 bar. So we can make P6 the subject. So P6 will be equal to 1.6 bar P7. And remember in our question or in our data, we were given the atmospheric pressure. And P7 will be equal to the atmospheric pressure. So which is equal to 1.013 bar. So we are multiplying it here. P6 will be equal to 1.6 multiplied by 1.013 bar, which is going, or which is giving you 1.621 bar, and this is the pressure which is entering the LPT, or low pressure turbine. Then now we can continue and have our Roman 2 question, which is saying that then we find the overall thermal efficiency. Overall thermal efficiency. So overall thermal efficiency is given by the network output over the total heat supplied. Total heat supplied. And our network output is equal to the work done by LPT. Our network output is work done by LPT. So we get work done by LPT as, so we multiply by mechanical, multiply by CPG, then T6 minus T7. We substitute, we have 1 multiplied by 1.15 into 973 minus 878.8 is our T7. And you are getting this as 108.33 kilojoule per kg. We continue and get the total heat supplied. Total heat supplied. This is equal to CC1 plus CC2. Then we have CPG T4 minus T3 plus CPG T6 minus T5. This one is for CC1 and this one is for CC2. Now we can substitute what we have: 1.15973 minus 821 plus 1.15 into 973 minus 667.3. Then when we solve this one, we are getting 174.8 plus 351, 351.5. 6, and the total it supplied will be 526.36 kj per kilogram K. Then now we can get the overall efficiency. Then overall efficiency becomes, now we take the network output, which is 108.33 over the total heat supplied, which is CC1 plus CC2, is 526.36, and this one gives you 0.206. If you want to give in percentage, you're going to say 0.206 multiplied by 100, and this one gives you 20.6%. This is how we solve the problem on an gas turbine plant. Thank you.